Hi, I'm Georgios Papaioannou, and in this video I'm going to share some insights on how to transform the physical archaeological object restoration process, and in particular the reassembly task, into digital twin, and exploit computational methods to provide and test hypotheses virtually in a non-invasive manner. First, we're going to examine the task at hand and explain how a computational approach can assist in the physical restoration process. Then we shall discuss the particular requirements and processes for the creation of 3D digital assets that can stand in for the physical parts in the virtual reassembly task, and finally, we're going to examine the workflows and possibilities offered by the digital twin. At an abstract level, reassembling a set of fragmented objects from a collection of fragments is like solving a 2D or 3D puzzle, where the number of target objects, the number of missing pieces, the shape and number of contact sites, and sometimes even the final shape are all unknown. Often, constraints such as planarity, texture, axial symmetry, or distinctive geometric features provide additional priors that we can exploit. Problem scaling, leading to the explosion of the search space, uncertainty and dispersion of fragmentary material can significantly hinder the work of the restoration personnel. So, why go digital? The obvious reason is that we can transcend the barrier and restrictions of physical space. We can effortlessly and repeatedly work with fragile and hard-to-handle parts, disregarding limitations of weight, physical support and distance, as applying the laws of physics is optional when working in virtual space. We can easily allow pieces to overlap, penetrating each other or float in empty space, because that happens to be more convenient during the experiment. Multiple object instances are readily and instantly available to us so that we can test multiple hypotheses and countless variations without damaging the originals. Physically dispersed objects can be digitized and brought into the same virtual space without moving them from the collection they belong to. Sharing and remotely accessing the digital versions of partial objects can greatly assist scientists to collaborate and advance knowledge. In a digital twin of a restoration process, we can never go wrong. The process is by definition non-destructive, and we can always undo a failed attempt or revise a decision in the future. Another important aspect of digital reassembly is the fact that we can go beyond the capacity of the human brain and sensory interface to process and objectively assess a result, because we can perform comparisons and measurements at an accuracy and scale unattainable by us. We may be good at qualitatively and comparatively appraising and roughly assessing a result, but not at quantifying things. Finally, we can enhance human perception by visualizing aspects of the objects that are not related to the colorization or lighting of the surfaces. Furthermore, with virtual objects we can see through geometry and inspect otherwise impossible to see surfaces as they are brought into contact with each other. So, what can a digital twin offer in practice? With a digital twin for computational and artifact restoration, we can perform non-invasive hypothesis testing at various levels. At the very least, a virtual space can provide visualization and manipulation capabilities for the manual alignment, object comparison, annotation, and progress and version tracking of the restoration process. This in turn enables the exploration of alternative scenarios and the exchange of ideas and recommendations. In a more intelligent simulation environment, an expert can perform assisted manual alignment, where a computational framework can provide geometric snapping and penetration-free pose optimization, measurements, and quantitative analysis. Cranking further up the computational involvement, a part alignment system can propose pairing solutions and estimate pairwise poses for the interlocking parts, or even recommend global sub-puzzle configurations, optimizing part combinations and multi-part alignment. So in order to enable all these, what does a digital twin of fragmentary material embody? First of all, we must understand that a digital twin by definition is a digital mirror of a physical entity or process under a specific operational environment. In other words, a digital twin is always related to a number of tasks, processes and workflows we can do either in real space or in virtual space. In this sense, a digital 3D asset needs to be as complete and faithful to the original as the restoration process demands. So a digital twin may not be necessarily better in terms of data representation than a digital surrogate of a physical object created for documentational purposes, as long as its morphological and appearance attributes serve the purpose of the intended task. To give a rather extreme example, in this scenario, only the contact surfaces of the two parts that are included in the digital twin for this reassembly process need to be thoroughly digitized, whereas other parts that are deemed irrelevant to the task may even be omitted. This by extension can significantly speed up digitization approaches if we focus on what is important for our workflow and disregard what is not. Furthermore, during digitization, captured detail may go well beyond the requirements of fragmentary material alignment and computational comparison, often due to the presence of erosion and general weathering of the physical parts, which anyway prevent perfect fitting. This means that typically, and to expedite computations, scanned parts are usually first moderately simplified. For object restoration, the curator of a digital collection would have already introduced some form of preclassification, labeling parts that form potential clusters or have been unearthed or retrieved from the same location. This preclustering is just as essential in the digital twin of the restoration process as it is in the physical counterpart, though. Depending on the level of automation one expects from the computational restoration pipeline, converting a simple 3D model to a reassembly-ready digital twin involves some augmentation processes that make the digital part more informative for the computational methods that follow. The first augmentation is related to the fact that when attempting to computationally align two parts, there are potential configurations of the two objects that produce a trivially maximal contact, while being entirely incorrect. A typical case arises when the two pieces have large, flat, or generally compatible intact surfaces. Obviously, a human would outright skip such a match as totally irrelevant, but without any prior, a computational method would attempt to investigate and even prioritize such a perfect fitting. To guide an algorithm away from such a pitfall, an optional yet effective preprocessing of the assets can be introduced. We segment the surface of the objects into regions that classify the latter as potentially fractured or not. During part alignment, only the surfaces labeled as fractures will be used for determining contacts, while the rest will only be contributing to penetration avoidance. False positive labeling is usually not an issue, since we only want to exclude the most trivially smooth or flat parts. Fortunately, in our case, these steps can be handled automatically by a reassembly system behind the scenes, requiring no user intervention. In the same spirit, the cultural heritage expert interacting with a digital twin may opt to provide additional constraints in the form of annotations that manually correlate to areas on the surface or even enforce a particular correspondence between parts. These metadata follow the parts and can be utilized during any automatic or semi-automatic reassembly simulation. In all but the most manual reassembly digital twin scenarios, an algorithm can operate alongside the digital heritage expert to perform powerful post-optimization, which is beyond the capabilities of even skilled 3D modelers, implementing the counterpart of careful alignment of skilled restoration personnel. Whereas humans mostly rely on extrinsic features, similarities, and context, a geometry processing algorithm excels in comparing and optimizing distances and performing intricate feature registration. In a digital twin for artifact restoration, a human expert and software collaborate to solve a puzzle. In this synergy, the role of the digital heritage expert may vary, depending on how tightly the user is involved in the loop. In typical computational reassembly methods, the role of the computing system is to analyze the provided pieces, measure the similarity and compatibility of part pairs, and provide recommendations about potential subassemblies. In such an approach, the user is involved in providing constraints, such as explicit couplings or prioritization of bonds between fragments, and in reviewing and modifying the computed recommendations. This rather limited role of the expert human has been often attributed to the non-interactive computational process involved in the pose estimation and clustering of the parts. However, this needs not be so, if we allow the expert user to take control of the process and explore part configurations assisted by the computational system interactively, by allowing simultaneous user-driven manipulation of the material backed by adjustments and recommendations provided on the fly. These adjustments can be more focused on the sub-problem that expert is currently attempting to solve, and therefore faster to resolve. In terms of data, in both simulation scenarios, the reassembly simulator ingests geometric and optionally the textural information of the parts, along with any metadata produced during fragment processing, and provides as an output the modified coordinates of the aligned pieces to be explored and used for visualization, reference, further analysis, or physical prototyping. And exactly this is the powerful implication of digital reassembly that makes such a technology a true digital twin. What you assemble and reconstruct in the virtual space can be made real by 3D printing technologies to assist in the physical restoration of the artifacts. Not only can one transform the assembled pieces into tangible objects that can be further studied, but the assemblies can drive additional virtual to physical restoration processes, including the production of highly detailed and accurate prosthetic parts. The Artemis project supports object restoration workflows and applications by providing a set of streamlined and intuitive online alignment services tailored to the task of computational part registration. The respective REST API enables the production of thin client applications that can take advantage of the Artemis infrastructure to set up and operate on collaborative digital twins for object restoration. Coupled with a rich semantic information network, remote rendering and annotation facilities, and powerful dedicated computing infrastructure, Artemis opens new possibilities for the next generation of collaborative virtual restoration tools.